Hello class, this is a video tutorial on differential calculus using the exponential function. By understanding and summarizing the applications of differential calculus, we can apply these in the near exact same way to the exponential function. Well, the different ways that we use calculus is to find the gradients of tangents of functions at any value of x. We can find the equations of tangents and normals. We can determine the location and the nature of stationary points, and determining locations of inflection points, and sometimes also the optimization problems. Well, just so we can remember, the derivative of e to the x is itself, and if e to the x is some function, so e to the power of 3x squared, the derivative of this is itself times the derivative of the power. So let's get straight to an example here. So we've been given a function f of x equals 2e to the power of x and a point a1 f of 1. So this point is on the function. Let's find the equation of the tangent at the point A and prove that the tangent passes through the origin. Let's make some space for ourselves here. So in order to find the equation of the tangent, just so we can visualize actually, let's just graph this very rough sketch. So here's my xy coordinate. 2e to the x, well, I know the exponential function looks somewhat like this. And let's say that the point A is here, so that's a f of 1, whatever that might be. And the tangent, it's saying that it actually, I know it's very rough, but you know what, let's move that point. Oops, I have to move that point. Because they're saying that the tangent passes through the origin. So let's say that that point there is, let's say that that point there is point A. Oops. So we want to find the equation of that purple line and prove that it passes through the origin. Well, before we prove it, we need to find the equation. To do that, we need the derivative. So if we have f prime of x, well, that's just this one here. So, well, that's going to be itself, itself times the derivative of the power. Well, the derivative of x is 1, and we need to multiply that by the coefficient that's already there. So there it is. In order to find the equation of the tangent, equation of tangent, so it should be a t, we actually need the point gradient formula because the tangent is a straight line. So we need y minus y1 equals m x minus x1. Well, we've almost got a point because we have the point 1 f of 1. So let's find y1 and x1 first. So let's find the point A. Well, we know it's 1 f of 1. Well, f of 1 is we substitute 1 into the function, 2e to the power of 1. That's just 2e. So the point A is 1, 2e. So we've finished this one. Take that off. Take that off. We just now need the gradient m. Well, the gradient m, the gradient m, we can find that using our gradient function, derivative, because this will tell us the gradient at point 1. So let's find f prime of 1. 2e to the power of 1, that's just 2e. Now we have the gradient. Now we can use this one. Let's move this down. Substituting all our values, it's going to be y minus y1, that's 2e, equals the gradient 2e, x minus x1, well, x1 is just 1. Expanding this becomes y minus 2e equals, expanding this, that's 2e times x minus 2e. Let's leave this in general form, so let's move the y and the 2 across. So it will be 2e to the x minus y, that's negative 2e, and by moving this to the other side, we're adding 2e to the other side, so those two actually cancel, which leaves us with, oops, let's erase all of this. So these two will cancel, leaving us with this equation of the line. So now, to prove that this passes through the origin, now remember the coordinates of the origin are 0, 0. If we substitute x equals 0 and y equals 0 into our function, we should get a true statement. Well, let's do that. 2e times 0 minus 0 equals 0. Well, that's 0 and that's 0. Which leaves us 0 equals 0. So we've proven that this equation of the line passes through the origin by substituting 0, 0. Okay, let's now move on to the next question here. Find the equation of the normal at point A. Again, in order to find the equation of the normal, we need the derivative. I'm just going to copy it from here. So we have the derivative. And to find the equation of the tangent, this time I'm going to make it the normal of the normal. Again, we need the exact same points. Y minus y1 equals m bracket x minus x1. We already have our points. Our point A is 1, 2e. We now need our gradient. Now, the normal is perpendicular to the tangent. So the gradient of the tangent, m1, is equal to 2e. And we know that for two lines to be perpendicular, the gradient 1 times the gradient 2 should equal negative 1. Substituting 2e, so that's 2e times m2. We can divide by 2e, so m2 equals negative 1 on 2e. Substituting all of the points, we have the point and we have the gradient. We can now use the point gradient formula. So y minus y1 is 2e equals the gradient negative 1 on 2e x minus 1. For this, I'm going to multiply by 2e on both sides. So this will give me 2ey minus 4e squared. This is, so that cancels out, leaving us with negative 1 times the group. That's negative x plus 1. Moving this to general form, we get, so I'm going to move x to this side. This becomes positive x plus 2ey minus 4e squared. Moving negative 1 to this side, we're left with minus 1 equals 0. Let point B equal the x-intercept of the normal. Now, we want the point B, we want the coordinates of the x-intercept. Well, the x-intercept, y is equal to 0. So we have the equation of the normal. We're going to let y equal 0. So that's going to be x plus 2e times 0 minus 4e squared minus 1 equals 0. That goes away, leaving us with x minus 4e squared minus 1 equals 0, which leaves us with a point x equals 4e squared minus 1. Now let's calculate the area of OAB. Let's grab our little sketch here. Let's cut it, put it back here. So we have this going on for us. Let's draw the normal. The normal will look something like that. And the x-intercept at that point was 4e squared minus 1. We know that f of 1 is now 2e. And this point here is 0, 0. OAB, so remember this is point A. That's point A. This is point O, that's the origin. And this here is point B. So we are now looking for this area here. Well, I hope you can see that this is actually a triangle where the base is that length, which is 4e minus 1, and its height is 2e because that is the y value of 2e. To find this area, we let a equals half the base, which is 4e squared minus 1, times 2e. For this, I'm going to expand the brackets first. Half, that's 8e to the power of 3, minus, so I multiplied that. I'm going to multiply the negative 1 now, so minus 2e. Halving everything on the inside, so I'm going to halve everything here. This becomes 4e cubed minus e. We can factor out 1e, so e outside of 4e squared minus 1, and that is our area. We don't know what unit this is in, so I'm going to put unit squared. And if we really want to, we can approximate this. Let's get an approximate value. E 4e squared minus 1. That's approximately 77.62 unit squared. So I hope you can see how even with E, we still apply the same concepts of finding gradients, finding the equations of normals, and finding areas as well from the intersections between two values as a triangle or whatever shape that it might make. Hope to see you in the next video. Best of luck.